And good morning. I think we're live. It says we've got 22 concurrent viewers and YouTube is currently showing that the stream is active. So, hey everybody. I hope you're having a nice Sunday morning or Saturday evening or whatever time it happens to be. Hey, thanks Incognito. So, sounds like audio is working. I'm wired up. Everything's black at the moment, so you can't see it, but there's a microphone attached to me on the front. Hopefully that will give reasonable quality audio. WVMBE said 2 a.m. So that would put you where? Somewhere in Europe? Saturday night here in Quebec. Cool. Oh, Belgium. Yes. Nice. Cool. Well, we'll give it a couple of moments while people join. But I had a couple of ideas about things that we could do today. Last week was a bit of craziness with walking around the room a lot and running the pick and place machine, and that was a really cool experiment. But one thing that I really need to do is have a better way of taking a camera and moving it around. What I did last week was use my mobile phone running as an IP camera and then had that connected over Wi-Fi. OBS was taking that in and then streaming it. But there were a couple of problems. One is that it was really laggy, so the video from that was a fair way behind what was going on. And also something that I didn't know at the time that I was doing the stream, and I noticed when I went back and looked at it later, was that the video was also stuttering quite a bit. So the moment where I crashed the pick and place machine, the camera stuttered just as the head was about to move, so you don't see the moment of the first crash before it went back and then crashed a second time, which is very sad. We didn't get to see all the damage. So what I need is a camera that will let me do proper streaming and also let me walk around the room with it without lag and without that stuttering. I'm wondering if just something like a webcam on a long USB cable would do the job. I might give that a try. And if anyone has suggestions on techniques for doing that, that would be cool. So, topics for conversation. One of the main reasons for doing this, as I've said in previous weeks, is to hear from all of you about how you are going. Are you going nuts in isolation, feeling okay? So if anybody wants to chat about what they're doing, go for it. Drop it in the chat. A couple of ideas. One is that just before going live on the live stream, a couple of us in Discord were talking about things that have gone wrong, like disasters that have happened. And Zagathi was just showing a 1-watt resistor that they were using in class. They connected it up to a variac, and another student wasn't careful and turned it up too high and blew up the resistor, and he's posted a photo of a 1-watt resistor with its side blown off. So there was there was a chat about things that have gone badly wrong, and I've screwed up many things, so it could be fun to tell those sorts of stories as well. And another interesting thing, so we might get back to that. There's okay, so Aaron just asked, what's the difference between your Ether 10 and Mega? Now that actually ties into the topic that I was just about to get to in a slightly different way, which is, what is the difference between a Raspberry Pi and an Arduino? And this came about because I got an email last night from a Freetronics customer who just sent me some information about some projects that he's been working on and how he'd started off using Arduino boards in a couple of things and then he switched over to using Raspberry Pi. And so he was talking about the advantage of using a Pi in terms of having a full computer stack essentially. So you've got the operating system And the advantages that he was talking about were being able to connect to it remotely, program in Python, update the code while the system was running, all of that sort of thing. And the difficulty of doing updates of devices once they've been deployed, if they're running on an Arduino board or other microcontroller board. And so Aaron's question kind of ties into that as well. And so this is something that I've talked about in the past in different contexts, but it's probably worth mentioning. So the major difference, okay, this largely comes down to the difference between a microcontroller or an embedded system and a full computer. And one of the questions that comes up quite a lot is people will say, hey, I can get a Raspberry Pi for somewhere in the same ballpark cost as a board like an Arduino or one of the equivalent microcontroller boards. So why would I use an Arduino, like an 8-bit microcontroller running at 16 megahertz with a couple of K of flash, not much storage, that sort of thing, compared to, say, a Raspberry Pi for, in the ballpark, the same price, when you can put gigs of storage on with a micro SD card. It runs at, I think it's in the order, I can't even remember, it's like a 1 gigahertz, 1.2 gigahertz processor with the current models, like quad core. It's got video on it, runs Linux, so you've got a full multitasking operating system. Why would you use an Arduino when you could use a Raspberry Pi? So my response to that basically is that even though they're conceptually sort of similar in terms of similar size, similar price, they are very different from an architectural point of view, which means they have different strengths. And if anybody wants to drop stuff in the comments on this, please go for it. I'll just give my thoughts on it. So the advantage of a Raspberry Pi are some of the things that I mentioned earlier. You can run a full operating system on it, which means that you can do things like run a service like SSH, and then you can log into the Pi and edit code on it directly. You don't need to run an IDE, connect a programmer to your target device, and then flash a new version onto it. You can use it as a remote access computer. And it's good in terms of mass storage because it's got the SD card. So if you're doing something like acquiring sensor data, you can write that to the SD card, store it locally. You've got gigabytes of storage. That's not really a problem. And that SD card, though, is also one of the downsides of a Pi compared to something like an Arduino. With a Pi, you're dealing with an operating system running on mass storage, which can be damaged because underneath the operating system, you've got the file system layer, which is managing reads and writes to the storage device. On something like an Arduino, you don't have a file, well, you can have a file system, depending on what you're doing. You can put an SD card in with an SPI interface onto an Arduino for storage if you want to. But the code that you're running is not generally stored on an SD card. It's going to be stored in non-volatile memory. And if you lose power, you don't have problems like an inconsistent state on the file system. One of the problems with something like a full multitasking operating system is that it's going to be constantly reading and writing from the disk. There'll be things like log files that are open and are being written to. So the operating system will have file pointers to the different files that are being used. And if you simply pull the power on this, you can end up with a corrupt file system. If you have a microcontroller and you pull power on it, nothing bad is going to happen, except in very unusual circumstances. So one of the major advantages of something like a microcontroller is that you can pull power from it, put power back in, and a second later it's going to be up and running. Well, depending on how the bootloader is set up, it could be back up and running your code again within milliseconds. Whereas if you pull power on this, you could corrupt the disk, and then when you put power back on, it won't be back and running in milliseconds. It'll be back and running in maybe 30 seconds, give or take, depends on what you've got running on it. So in terms of building something that you want to do, one simple job, install it somewhere, and then not think about it for years, a microcontroller is a much more robust way of doing it. This is really a full computer, which is ideal for other purposes. Like if you wanted to generate charts of data, you wanted to run a web server, then something like this is better than an Arduino. Even though you can run a web server on an Arduino, it's very limited. And also I should point out that I'm using the term Arduino here in a very inclusive way. What I'm using it to represent is microcontroller modules or boards that could include something like, ESP8266, which can have more storage on it. It's got Wi-Fi. The ESP32 has dual cores. Yes, it's got dual cores. So there are certainly very powerful microcontrollers as well. And I kind of fall into the lazy habit of just saying Arduino when I mean a board that's not necessarily programmed using the Arduino IDE. It could be programmed with other things as well. Another major difference, two more major differences, and then I'll stop on this theme. One more major difference is power requirement. For this to run, it takes typically in the order of a few hundred milliamps, could be up to 500 milliamps if you don't really have many peripherals plugged in, whereas a microcontroller could take a few milliamps. So this could be pulling 100 times more power than a microcontroller, and that's just because it's trying to do a whole lot more stuff. So 4 cores running at a gigahertz takes a whole lot of power compared to a single microcontroller running at 16 megahertz. So the final thing I'll say about this is that the I/O on something like a Raspberry Pi is fairly limited, and that's because it's just some general digital I/O pins. There's I2C and that sort of thing, which is interesting, but it's not really intended for building into something else and relying directly on the I/O of the board. What you would do typically is rely on some other peripheral to do the I/O for you, and the I/O is going to be very dependent on what you're connecting it to. Whereas a microcontroller, and this is kind of a one-size-fits-all thing, whereas with microcontrollers, most microcontroller ranges will have a common core, like the 18 mega core, for example, in the simple Atmel line of microcontrollers, like on the Uno and Leonardo and those sorts of things. And the core will be the same, so it will run the same code, but there will be variations in peripherals. And you see this, this is really obvious in things like the PIC line of microcontrollers as well. There can be a very wide range of options in the microcontroller family. So you can have a single type of microcontroller, and you can say, I want a version that's got 4 UARTs and a whole lot of digital I/O, or I want a version that only has 1 UART, but it has built-in USB host support, or I want one that's got a whole bunch of analog inputs. So what you can do is pick the specific processor that you want, depending on the peripherals you need, and then design that into your project. So the comment from the email that I got last night was saying that I seem to favor Arduino boards a lot, and I think my answer to that really is my preference is to use whatever is appropriate for the problem that I'm trying to solve. And many times a Raspberry Pi or something similar to it is the correct solution when you want a full computer stack, but many times it's not. So you really have to look at what you're trying to achieve. For example, with my light switches, if I wanted to have a light switch that would do things like drive RGB LEDs in the switch and detect button presses and send events back. It doesn't make sense to build a Raspberry Pi into every light switch, but you can put a $2 microcontroller in there and it'll be much more robust. The code generally doesn't need to change once it's been deployed, and it'll just run for years. And if you pull power from it, plug power back in, it's just going to come back and keep working. So I love I love little single board computers like this. I think the Raspberry Pi is amazing, both as a device in itself, but also in terms of what it kicked off, because there have been so many other boards that have come out. I mean, there are obvious boards like the Orange Pi and those sorts of things, but then there's the BeagleBone series, which I think predate the Pi and have continued to be updated since. It's not just one solution. If you're looking at little complete computer stacks like this, you've got many options. So for many purposes, that's fantastic. And I use many of these around my house and in different projects. But as I said, the idea is to try to pick the solution that is appropriate to the problem you're trying to solve. That's what it comes down to. So let's have a quick look at some of the comments and catch up. So, and Aaron's original question was, what's the difference between the Ether 10 and the Mega? So I assume, Aaron, that you meant the Ether 10 and the Ether Mega. The difference is the I/O. They both have Ethernet, they both support power over Ethernet. The difference is that the Ether 10 is like an Arduino Uno, so it's got an ATmega 328 on it with Ethernet. The Ether Mega is like an Arduino Mega, so it's got an ATmega 2560 on it plus Ethernet. So the Ether Mega is basically just the same thing, a bit more memory and far more I/O for projects where you need that. Oh, one other difference. This is actually an important one. The power supply on the Ether Mega is a switch mode power supply, which means that if you put in, I don't know, say 18 volts or 20 volts into it, the switch mode power supply is quite efficient and it doesn't get very hot. So it works quite well with power supplies that are up towards the upper end of the voltage range of what it can accept. The power supply on the Ether 10 is the same as on the Uno. It's just a linear regulator, which means that it cuts the power by dissipating all the excess as heat. And that results in running hotter if the voltage is well above the operating voltage. So if it's way above 5 volts, that difference is going to be dissipated as heat. Okay, so Viatech said Arduino can handle power outs, Pi's not so much. Yes, exactly. And Viatech also said, overclocked my Pi 4 from 1.5 GHz to 2.1 GHz with an ice tower cooler. Yes. I have, I think, just about every Pi model from the very early Model A that first came out. And the first one that came out, I think, was single core and not particularly fast. I think from memory it might have been around 800 megahertz. And I did try running that as a desktop just to experiment with it, and it felt really laggy. But the amazing thing is that with the current Model Pis, like the 4 series, they are so fast, it's crazy. You can very legitimately use them as a desktop machine and not feel like you're missing out on very much. Mladen said, I just watched the video from 2017 when I showed the new reflow oven. And says that it's 1 AM in the UK. Well, thanks for staying up late or getting up early. Yeah, 3 years? So it's been 3 years since I've had that reflow oven. Doesn't seem that long. Time flies. Richard had a couple of comments. He said, the microcontroller versus microcomputer. While a microcontroller can be adapted to many different tasks, it's closer to the actual task than a microcomputer. usually one, maybe two at a time. Yeah, that's right. So you're not abstracted away by the layers of the operating system and everything else. The code that you're running. Yeah, so this is getting to a very important point, which I should have brought up earlier. And then Richard said, even when the user dedicates it to a specific task, this is a microcomputer, it's usually actually doing many different tasks. There's an entire OS underneath. Yes, exactly. And with a multitasking operating system like Linux, what it's doing is switching its attention very rapidly between a whole series of things, which means that at any one moment in time, it's not necessarily paying attention to a particular process. So if you need to be able to do things like react extremely rapidly to I/O, like to decode a bit stream, for example, and do the timing for that in the processor, many times a microcontroller will do a far better job of that than a larger and supposedly more powerful computer, because the more powerful computer is running its operating system, it's switching tasks, it's doing lots and lots of different things all at the same time, whereas the microcontroller is doing absolutely nothing but sitting there and watching that I/O pin, and it can measure the timing down to whatever the resolution is. It's very small, microseconds. So even on a slow 8-bit microcontroller, like an ATmega 328, you can do microsecond level timing on I/O pins and then do analysis of the waveform. So it's better from that sort of thing. WVMBE said, if you would put a touchscreen on a Pi, how much distance can they be apart? I noticed that if you add a Pi in a wall, they can become very hot, especially the Pi 4. Exactly. So a Pi will typically be pulling a few watts. Now, in terms of a touchscreen, there are a couple of different ways they can be done. And some of them, I'm just thinking about the different ones I've seen. I've got a couple myself. In fact, if I move my head right there, that is a Raspberry Pi with a 5-inch touchscreen on it. And I use that with Octoscreen for controlling that 3D printer, which is really cool because I can just walk up to the printer and use the touchscreen, select items, and print them out of Octoprint. And touchscreens can be based on a couple of different technologies, and they can also interface with the host computer in a couple of different ways. So the simplest form of touchscreen is a resistive touchscreen, which has a couple of layers of a membrane in front of the screen, and they have 4 electrodes. They'll have one electrode, basically one at each side of the screen, so top pair and side pairs, and they've got 4 wires coming out of them. And by measuring the resistance across the pairs of electrodes, when you press something against the screen, it will it'll conduct basically between the electrodes, but the amount of resistance between the various pairs of electrodes will allow you to calculate the X and Y coordinates, so you can figure out the position. So those really cheap, things like the Nintendo DS touchscreen, that's how they work. And it means that you need to physically deflect the surface of the screen a little bit. The screens that feel like they're kind of plasticky, like soft, those are typically resistive touchscreens. And what you need is something like a microcontroller connected to those 4 pins to be able to detect changes in the resistance between those electrodes and then figure out the coordinates. Now with something like that, you can put the touchscreen at a bit of a distance from the device. And what I'm talking about here is not really the screen, it's the touch layer over the top, because you really have to think about it as 2 different things. If you're building a touchscreen, there is the display portion of the screen, which is what you think of as the screen, and then there is the touch sensitive system, which can be sandwiched on the front of the screen and you're just looking through it when you see the screen, or it can be built into the assembly. But conceptually they're 2 different things. And the connection between that particular touchscreen, wherever it is there is a microcontroller on the back of the screen which is doing the job of reading the sensor, and then the touchscreen assembly, which includes both the display part and the contact detection part, is connected back to the Raspberry Pi. And there are two connections because it's two subsystems. One is the HDMI connection. There is a little dog leg, it's like a U-shaped HDMI connector. So you plug it into, when the Pi is mounted directly on the back of the screen, there is an HDMI connector here, and there's another one right beside it on the screen. You plug the connector in, and then HDMI drives the display. And the display will work with no knowledge whatsoever of the touch portion of it. But the touch portion communicates through the header, the I/O header on the Pi, and I believe that screen works by SPI, I think. I just plugged it in and loaded the examples and it worked, so I didn't pay all that much attention to it. And the controller that is picking up the touch sensitive region on the front of it is then communicating by SPI to the Pi. So if you wanted to take that particular touchscreen and mount the Pi somewhere else, what you would do is you would need a longer HDMI cable for the video portion of the connection, and you would also need to extend the connection to the microcontroller that is attached to the back. Now with SPI, it's not really designed to go long distances. It's intended to be a fairly fast peripheral interface, but in the context of peripherals that are directly on the board, like an SD card, for example. So what a lot of people don't realize is that an SD card is just an SPI device. It's basically like a memory chip with an SPI interface in a little removable package. And the pins that are exposed in the micro SD slot are an SPI interface. So that's the sort of application that SPI is designed for. It's for rapidly transferring data between things that are in very close proximity. It's not equivalent to something like USB, where you have a peripheral that might be a mouse on the end of a wire. With SPI, you're talking about much shorter distances and much higher speeds in terms of data throughput. So how you would do that in terms of putting something like a Raspberry Pi more remote from the touchscreen, you might have to use some other method to connect it rather than rely on SPI. Or if you so off the top of my head, I don't really have a solution to that problem. Just thinking about how to do that. But what I would probably do is go back and re-examine what it is that you're trying to achieve and whether the architecture of what you're putting together is the right solution. And now I don't know quite what it is that you're working on. So if you're talking about something like a home automation system where you're wanting to build a control panel on the wall with a touchscreen and a Raspberry Pi behind it, that does give you a lot of flexibility, but I haven't done that. In the past, what I've done is used things like Android tablets attached to the wall, and in my house I've actually got a couple of Windows Surface tablets, really old ones. There's one attached to the wall in my kitchen, and that basically that means that you don't have the problem, because all you need to do is get power to it. It's got Wi-Fi already. You can run Ethernet if you want to, but things like tablets are already designed to be very thin, so you can surface mount them quite easily and they don't look too bad. Whereas something like a Raspberry Pi with a screen attached to it, you're going to have to cut into the wall and have this mounted behind it. NDX Gaming said there are a lot of touchscreens with control via USB. Yes, that's true. Yeah, and I didn't even get into capacitive touchscreens. I was just talking about resistive touchscreens. The systems that are, like that one up there, that's a capacitive touchscreen, not resistive. So it's a different thing entirely. So don't know if that's answered your question. I kind of went on a tangent there. Cool. So, Daryl made the point once again about the difference between a microcontroller and a little computer. Separation of concerns: ESP8266, 32 IoT, single job, so easy for large numbers. Raspberry Pi, central computer, easy to change what it does, but more flexibility. Yeah, that's a great way of putting it. It's they're different components of the system that work together, and they solve different parts of the problem. So L4 Tube says, is the RFID in your arm still working, and do you use it a lot? Is it worth it? Yes, it's still there. I've got to go and look up the date of when I put it in. I think it's been about 13 years, maybe it might be heading towards 14 years since I put it in. And yeah, it still works just fine. Because it's a passive transponder, it doesn't have any kind of internal power source. It leaches power off the field of the reader, and then just returns. How much do I get into this now? Probably not much. It causes modulation of the field that has been generated by the reader, and then the reader can detect the modulation, and that's how it gets the communications happening. Summary is, it still works, and it should work for the rest of my life. The difficulty is that it's very old technology. There's no encryption on it. If you think about what mobile phones looked like 13 or 14 years ago, or what computers were like 13 or 14 years ago, that's the sort of technology that is implanted in my arm. And even when I implanted it, it wasn't new. It was a type of chip that's it had been around for many years at the time. So it's probably 20 or 25-year-old technology. So the result is that it still works just fine, and it should work as long as I do, but it's extremely limited compared to a lot of the stuff that is being done now. Like some of the implants that are being done by Amal over at Dangerous Things are really cool. They use much newer technology, and you can do things like make contactless payments with them. There are some things that he and a friend of his were doing a couple of years ago now with taking data from a biometric passport and loading it onto an implant so that at passport control you could scan. But let's not get into that right now. The Guru says, I bought some blue pills and have yet to find a project for them. Pretty dependent on ESP boards. Yeah, I haven't used a blue pill. I've seen, I know people that have, and they seem like pretty decent little boards, but I've never actually used one myself. And yeah, your comment about being pretty dependent on ESP boards. One of the traps that I fall into, and I think a lot of people fall into, is it's that old thing of when you have a hammer, everything looks like a nail. When you first get into Arduino, you learn about a particular type of board, and then you want to solve everything with that board. And so I tend to use AVRs in lots of places where other types of microcontrollers might be more appropriate if you're being totally objective about it. And it's largely because it's what I'm most familiar with. I used to use Pix a bit, a long time ago, like 20 years ago. I used Pix, like the Pix 6, well, I'm trying to think back to part numbers. Pix 16F84, I think. I used in a few projects maybe 20 years ago. And from what I've seen, the PIC range has some advantages in terms of the peripherals that are built in. PICs tend to have really good options in terms of things like saying, I want a combination of this, this, and this, and they'll have a microcontroller that has exactly that. Whereas the AVR range in the past has tended to be much more limited and rely on external peripherals. But because I've done so much work with AVR, starting with the very early Arduino boards, then that is the hammer that I use to solve lots of problems. But and in recent times, it's the ESP8266 that I use to solve lots of problems. Whenever I'm starting a new project, I think for about 5 minutes about what my peripheral requirements are going to be, and then I slap an ESP8266 on it, or an ESP32, or an AVR. Like I use the ATmega32U4 quite a bit, just for its USB interface. And I have a feeling that in future the ESP32S2 is likely going to be one of my favorite chips, because it seems to have that good balance of having the USB host functionality built in. It's got the architecture of the ESP32, but with only one core, not two, and many of the other advantages over things like the ESP8266. But I haven't actually got my hands on an ESP32S2 yet. I know that Sion, the unexpected maker, has already designed a board, at least one board, maybe several boards with it, and he's got some of the silicon from Espressif, and it looks really cool. So I think that will be a good one for the future. Ooh. Adrian said, I bought your Freetronics watchdog circuit for my autonomous boat project. Oh, that sounds cool. I really like maritime projects. So, Adrian, if you want to tell us more about that, you can here, but probably a better place is to jump into the Discord and have a look in the Share Projects channel on there. So, while I'm talking about that, I keep pimping the Discord because it's turned out to be such a cool place to talk about things and see what people are up to. And in fact, while this live stream is on, a couple of people, including Guru, are posting pictures. Oh, and who else is in there? Ooh, there's a render of a of a laser cutter being built. There are some pictures of fun things. So if you want to continue chat outside of these live streams, check out that Discord server. And yeah, so I used to sail a lot. My dad has been into boats pretty much his whole life, and back when I was up to the age of, I think, about 7 years old, he built a little sailing dinghy in our living room, and so that was a mirror sailing dinghy, and that can't have been too good for family harmony. But basically, he used the living room as his workshop and built a dinghy and then took it out sailing. So he's owned many different boats over the years, and I've been sailing with him since I was very little. And then in my late, in my mid to late teens, I sailed a lot with my old school friend Brad. We used to race Tornado catamarans down at Sorrento Sailing Club, and went around and competed at a few different places sailing Tornadoes. So I really like being out on the water, but I haven't for a very long time, which is quite sad. But anyway, back to this autonomous boat. I would like to know more about that. So please jump in the Discord and let us all know a bit more about how that's going. I'm curious to know what the autonomous side of it is all about. Like, are you using ArduPilot or ArduBoat well, technically I think ArduRover is what's mostly used on boats. But I'd like to know more about that. Okay, so back to the touchscreen thing earlier. WVMBE said, I want a touchscreen for controlling HA, which I assume is Home Assistant. Could be home automation, but probably Home Assistant. So yeah, I don't know. You can get some really cheap tablets now. You look at, this is one of the things that's kind of weird, is you look at dedicated home automation touchscreens. Like if you want to get a Clipsal C-Bus touchscreen, for example, those things cost a fortune. And you can go down to your local supermarket and buy an Android, like a 7-inch or a 9-inch or whatever it is, Android tablet for $50, $80, and it'll be quad-core processor, it's got Wi-Fi in it, it's got a battery in it, which means it's got battery backup, so all you have to do is run power into the back of it to keep it charged, and if you have a blackout, it still keeps right on working. Those things are incredible. Because they're produced in such large quantities for a mass market, things like little Android tablets are a great solution to many problems. And if you think about the idea of buying a $50 Android tablet that is maybe 7 or 8 millimeters thick, and sticking it on the wall, you give yourself a big touchscreen interface to whatever you want to pull up on that screen. It solves an awful lot of problems. I mean, in the early days of doing my own house, doing DIY touchscreens was something that I was really interested in as well, and I ended up just getting, I went down to the local Officeworks, and they have a couple of recycling things out the front, so people put in their old mobile phones and that sort of thing, and I went dumpster diving a little bit and found an old Android phone and brought that home, and it worked. So I actually had an Android phone stuck on my wall. In fact, it was right there for a long time. There was a little black Android phone where that light switch is. And that was my touch interface. So what I did was I ran a full screen web browser in Android, and that loaded an interface that was being served off a computer that was running the home automation system. It was just running Apache and PHP and MySQL, the whole typical LAMP stack. And that was serving up an interface that was then displayed as a full screen browser window on the phone. And when you tap something, it would send, it was using asynchronous JavaScript to send events back to the controller, or back to the Linux box, which would then do whatever it needed to do, like MQTT messages or whatever. So yeah, I've turned into quite a fan of little Android touchscreens in different places. AB said, tangents are good. I use them all the time. Yes, I do too. I use the tangent tool in Fusion 360, and I use them in real life as well. So Aaron said, what's your personal preference on programming languages to use? Ooh, this is an interesting one. What I tend to use, that's a very broad question as well. It falls into a couple of different classes, and that is the language to use on embedded devices and the language to use on like a full stack computer, which are typically not the same thing. I tend to go more for interpreted languages on computers. I quite like Python, but I'm not very good at it. I haven't spent much time using it. My my kind of confession is that I spent more than 20 years, or something like 23 years working in the PHP world. And in fact, I started using PHP before it was even called PHP. I started using it, when would it have been? It was in the mid-90s, and it was when it was called PHP/Phi. So, as in FI, for Forms Interface. And it was when, Rasmus originally created PHP/Phi as a way of doing server-side processing for his personal website. And he wrote it as a series of little utilities that you could call, and it had a couple of different components. And doing things like handling the form was different to the back-end processing, which is why originally when he did his first release, which was technically 2.0, I think, so the very first time he released the code, it was PHP/Phi, PHP/Phi 2.0, because the 1.0 version was what he had been using on his personal site. And I started using it, I think, within about a month of him releasing it. I was running it on a Sun Challenger S server, I think, at the time, and running it with MiniDB. So this was before MySQL and those sorts of things existed. And I kind of got into that whole ecosystem. So from the time PHP/Phi 2.0 came out, I was pretty much stuck using that. And so I've done decades of PHP development. And the result is that my brain just automatically goes to solving problems with that particular hammer, because that's what I'm most familiar with. But I do use a variety of things on the server side. I've done a bit of Perl in the past as well. In fact, quite a long time ago, I was the maintainer for a moderate-sized program written in Perl, because I used to be a Debian developer, and I maintained the Debian packages for a few Perl programs. And I wrote a couple of Perl programs mostly related to network administration and packaged them for Debian. And also in fact, I think that was written in C. I was thinking of the LCD proc driver. I was a maintainer of that for a while, but that was written in C. So on a proper computer, I tend to use either PHP if it's going to be something with a web interface, or Python if it's something that's going to be run locally. I haven't used Perl for anything new for many years now. A bit of stuff in Bash, a bit of stuff in C, and I don't know, there are other things as well. Like way back when I was at uni, for example, we used to use Pascal. I haven't used Pascal for a long time, although fairly recently a contracting customer came to me and said, we've got this system that needs to be updated, and the person that wrote it died many years ago, and it's written in Delphi. So those sorts of skills can still be useful from time to time. Okay, for embedded systems, basically C is the simple answer. I keep having people saying, use Rust, use MicroPython, all these sorts of things. And there are many other options. But once again, I'm in that situation where the hammer that I'm most familiar with using is C. So that's what I use. And MicroPython is very interesting. I have kind of hacked around on a few projects written in MicroPython, and in fact the originator of MicroPython is from here in Melbourne, and when he's in Melbourne, he lived in the UK for a while, was a member of the same hackerspace as me, and also Sion, who is a MicroPython expert. So if you're interested in that sort of thing, make sure you go and check the Unexpected Maker YouTube channel. He talks about, he's got a series of tutorials on MicroPython, which is really cool. Other things like Rust seem really interesting. I would really like to sit down at some point and try building something using Rust, because it looks like, so my outsider's view, not having actually used it for anything, it looks to me like someone who knows all of the problems with C sat down and tried to design a language that avoided those problems. And I just like to see what that's like. I think one of the big problems is adoption and how widespread something is. One of the things I really like about the Arduino ecosystem is the number of examples and drivers and things that you can get for just about any hardware. So if you are bringing up a board and you have a combination of a couple of sensors, and maybe you've got like addressable RGB LEDs, and you want to do some MQTT, there are libraries for all of those things, and you can just pull them in and call them at the right time, and you can very quickly build systems by taking those modules or subsystems and using them as you need to. And with something like Rust, because it doesn't have the level of adoption, then there might be issues with things like drivers. But I still really want to give it a go. It seems kind of cool. Okay, so Adam said he's working on that right now. I'm using an Android tablet with the Wi-Fi enabled. Set a browser window to point to your HA session and make a custom card that fits your tablet's needs. Yeah, that is basically what I did, except that I wasn't using Home Assistant. I was using my own dodgy homebrew system at the time. So I wrote the web UI using PHP to generate the page, and then JavaScript on the client side with asynchronous JavaScript updates, to using WebSockets to update the display when the status changed on different elements. So you could have a button, for example, for a light, and have the state of the element change when the server updated the state, and if you press it, it would send an event down and change the state as well. WVMB said, I don't like Wi-Fi for home automation, probably due to my IT background. Yes, a rant that I have been on many times. I'm with you on that. So for many tablets, if you want to connect via cabled Ethernet, they often have a USB interface on them that you can plug in a USB to Ethernet adapter, and you can cable the tablet. So the trick is doing that in a neat way, because typically the connectors on tablets come out of the bottom or the side or somewhere really ugly, and ideally what you want is for it to come straight out the back of the tablet, so you can drill a hole in the wall, stick the tablet on, and have the cable go in through the back, and then nothing is visible. So you can do some mechanical hacking to make that work. But yeah, okay, so I pull stuff apart, made the comment, I did a Raspberry Pi with a large Acer 23-inch cap touchscreen. It was a nightmare. It didn't work out of the box, but eventually got it working better off with an Intel compute stick. Interesting. Okay, yeah. On the Discord last week, I was telling the story of a very big home automation project that I was very peripherally involved with, and a particular demo day that we did. Now, in that home automation project, the way that was done, so this project was begun, it must have been 25 years ago, and things like Raspberry Pis didn't exist. It wasn't even that easy to get touchscreens. Like, the idea of a touchscreen was a really exotic thing. It almost didn't exist. And typically the way it was done was, and there weren't LCDs, so typically what would be done is you would get a CRT, so you get a flat screen CRT and then put a thing over the top of it, which was usually a light grid. So there would be light sensors on the edges, and you put your finger in it and it would detect the position of your finger by which of the beams was occluded. So really primitive by today's technology, but that was all that was available. In this particular home automation system, because the guy who owned the house had certain connections and had made some people lots and lots of money, he had a whole lot of sun servers running his house. So down in his basement, he had, I think originally 2 full-size racks, so 42 units high, a bit over 6 feet high, and they were full of Sun Microsystems servers, and that was what was running his house. So he had Sun servers, and then embedded in the walls he had these touchscreens. But of course, because the touchscreens were so physically big, it's not like it was a 7mm thick Android tablet, the walls were modified. They had a big hole cut in them with a box built into the wall. There was a monitor stuck inside it, and the touchscreen overlay fitting on front of it with a bezel so that it looked like it was all flush to the wall. And the interesting thing was that it was all open from inside the ceiling. So this is the place where I was telling the story on the Discord last week, where I went inside the ceiling. I was given a tour of the ceiling the first time I went to this house, and the walkways in the ceiling space all had chipboard laid in them, so you could just walk down it like a hallway, and there was a coffee machine in there, so you could sit up inside the ceiling and have a cup of tea or coffee and a biscuit, because people had spent years working in this house and they'd customized the hidden spaces to make it comfortable for themselves. And what you could do is, from inside the ceiling space, look down. It was like a vertical channel that would go down to the back of the touchscreens. And then there was a PC, I think from memory, yeah, there was a PC sitting inside the ceiling space, just like on a piece of wood, with a VGA cable going down, and I think it was probably a serial cable going down to the touchscreen. So it just went down this hole through the wall and into the back of the box where the touchscreen was mounted. And so he had these in every room of the house. That was really doing it the hard way. But it was long before common devices existed, and by the time I had anything to do with that house, they didn't have 2 racks full of Sun servers anymore. Over time, of course, things get faster and cheaper and smaller, and they had shrunk their 2 racks of Sun servers down to, I think it was like a couple of rack units of fairly standard sort of hardware that was doing everything that all the Sun servers had been doing previously. If you were in the Discord, I posted a private video showing helicopters landing at that house for a demo day. Anyway, that would just be rehashing a story from last time. So, I am getting behind on chats, way behind on chats. Let's just see what I'm kind of just skipping through. So if I know that in previous live streams I've missed questions, people have asked things, and then later I've scrolled back through the chat and seen a question and I thought, oh, I wish I'd seen that. So if I miss anything you say, I'm sorry, I'll do my best. But I'm kind of just scanning through the comments here, so I may miss some. So Dodgy made the comment, only problem with touchscreens everywhere is you are back to distributed computing. Kind of, in a way. It depends what you use the touchscreens for. If they are just like a window onto the system and there's no logic within the touchscreen, then I think that's okay. I see it as being a bit like pulling up a UI as an ephemeral thing and just making it permanent. And if it goes away, then you haven't lost any functionality other than that particular touch surface that can be replaced. So yeah, it's more to update. And this also comes down to one of the differences between a microcontroller or embedded system and a full stack computer is updates. With something like a Raspberry Pi, because you're running a whole lot of services, it's big, it's complicated, there are lots of attack surfaces, and so you need to make sure that you keep it secured and updated. Otherwise, you're going to be leaving yourself open to all sorts of problems. With a microcontroller, typically the possible attack surface is very, very small. And this is one of the things that I think is actually a problem with a lot of IoT devices now, is they are sacrificing development time for speed to market and going for using systems that are more than they need, which then opens it up to all sorts of problems. Now, a classic example is something like an IP camera. And we've all heard of the problems of IP cameras being open to the world and people loading malware onto them and those sorts of things. And that's because things like embedded Linux systems now are so cheap that from a manufacturing point of view, you can think, I can build a complete custom system from the ground up, like write all the code, and it'll take me X, person years of development to get to market. Or I can buy an off-the-shelf Linux module. I can run Linux on it, and it's already got all the video processing stuff. It's got support for networking. I can do config on it by putting a GUI on it, and like a web interface, for example. So you could be running a web server on it, and all of this stuff kind of comes free with the module, and it cuts your time to market because you can take a heavyweight solution and glue it into your product, and then you've got something that does the job. Most of the problems have been solved for you. The problem is it exposes you to future problems because all of these services that are running need to be kept updated. If there are any flaws that are discovered in them, you need to apply security updates. And how many people update the firmware in their IP cameras or whatever devices that you install around the place, and then it should just work forever and you should never have to care about it. You see this with things like routers as well. A typical domestic. If you go to most people's houses, they'll have Wi-Fi, and it will be something like a D-Link Wi-Fi access point router sitting in the corner somewhere that they bought down at Officeworks and they plugged it in, and it's never had an update since. So even if the manufacturers are diligent about supplying updates, the typical end user is not going to be staying on top of that and applying updates. So you end up exposed to known security vulnerabilities. Whereas with a system like a microcontroller, which typically doesn't have writable storage, which in itself removes a whole lot of potential attacks. The fact that it can't be updated remotely is often an advantage in that case. You can generally rely on them to keep working without being compromised for longer. Okay. Fortran, Allsop69 said, so Fortran and COBOL it is then. Yes, I've actually done coding in both Fortran and COBOL, but that was back when I was probably 12 or 13 years old, I think. I got out some, so this was back in like early 80s. I got out some, I went into the library actually and borrowed books about Fortran and COBOL because I was interested in it. And every now and then you get this whole thing coming back up about COBOL, and we have a lack of COBOL programmers because the systems that were written 30 years ago, 40 years ago, everybody that wrote it is now dead. and now we need to change our business logic, and nobody understands it. So that topic seems to come up again about every 5 years or so, and every now and then I think, I wonder if it's worth brushing off some COBOL. Theotech said bash for server-side stuff. Yes. I have written some crazy stuff in bash, and I think most people that work in IT have done that. Yeah, I won't go into that. Oh, Dodgy says VB6 all the way. Yep. And you don't mean Victoria Bitter. Visual Basic 6. Oh yeah, Sea Breeze. None of the COBOL rubbish. Turbo Pascal all the way. Yep. So I did some Turbo Pascal back at uni. Okay. Oh, here's an interesting question. Peter Kirkos said, please explain the benefits of an RTOS versus Arduino flavor of C. That is a really cool question, and I would like to, I probably want to do something about this as a video or multiple videos, because it's a really important question. And so what this means, for those of you that don't know the acronym, RTOS stands for Real-Time Operating System. And what it means is, trying to think of a simple way to explain this. All right, in a typical Arduino program or any like simple C program, the general program flow is that you initialize some structures. So you do some initial setup. And if you think about this from the point of view of an Arduino sketch, you have the setup and the loop. The setup is where you put your code that you want to run once, like setting pin modes and opening the serial port and that sort of thing. The loop is where you put code that you want to run over and over again. And if you watched my most recent SuperHouse episode, which was the code walkthrough for the air quality sensor, you will see that I have kind of hit a middle ground between just a basic C program and what you would want with something like a real-time operating system or a scheduler. And I've erred on the lightweight side, which is closer to being just a basic C program. So with the normal C program, what you will do is have the loop which iterates as fast as possible. So inside your loop you put a series of logic structures that do the different things you want. You might be reading from a sensor, reading from a I/O pin, like from a button or something. Could be writing out to something, like writing to a display. And you just want that loop to go as quickly as you can. Now, the issue comes where you want certain things to happen at certain intervals. And this is where you have something like a scheduler. So you might want to read from, so say you're not using an interrupt. Imagine that you're wanting to read from a button or a sensor. Say you're making a door open sensor. So you want to detect it as soon as it happens, and you just keep reading it over and over again as quickly as possible. But something else you want to do, you only want to do occasionally, like send a status update published to MQTT. So in your loop, what you can do is have a call to check the sensor that you're reading, and then you have a call to publish to MQTT. But if you simply do that, what happens is that it'll run through as quickly as possible, and it'll just be publishing to MQTT repeatedly. Now, the simple non-solution to that, and this is where beginners often get tripped up, is they use delays in places they shouldn't. So you might have a reading from a sensor as fast as you can, publishing to MQTT every 2 minutes. So you get to the point in the code where you're publishing to MQTT, you publish, and then you put in a delay for 2 minutes, and the code just sits there and does nothing, and then it goes around and it reads from the sensor again. The result is that you are now only publishing every 2 minutes, but you're also only reading your sensor every 2 minutes because the loop has this long delay in it. So the way I got around that in the air quality sensor code is I put timestamps on the last time certain events had happened. So as it's going through the loop, it can read. The idea is to never impede the loop. You want to keep it running as quickly as you can. So in the case of an event that you want to have happen every 2 minutes, what you can do is store a global variable that says the timestamp of the last time that thing happened. And then each time you go through the loop, you check the time and you say, has it been 2 minutes? No. Okay, don't do anything, just move straight on. So the loop just keeps going as quickly as it can. And then when you get to a point where it says, yes, 2 minutes has passed, you do the thing, like report to MQTT, you update the timestamp, and then you can move on and keep going through the loop again. The result is that you can have multiple operations that are being called in the loop. Some of them will be called every time you go through the loop. Some of them will be called at certain time intervals, and they don't need to necessarily be related to each other. And the loop is still running unimpeded. There are no big delays in it. So that is the kind of the minimalist approach to having a scheduler, but it's not a real-time operating system. What this does is allow you to defer certain things for periods of time. The next step beyond that is to have something like a proper scheduler where you say, I want to execute these particular tasks and they need to be done at a certain interval. And this is where you start getting into real-time operating systems like FreeRTOS, and there are a heap of them, but FreeRTOS is probably the most well-known, where you and also FreeRTOS is the basis of the ESP IDF. So when you set up tasks inside ESP IDF, you are specifying that you want certain things to be executed at certain intervals. That is setting up tasks within FreeRTOS. And then FreeRTOS is like a supervisor that it's like a loop that's running for you. So instead of having to have your own loop where you say, I want to do this, and then this, and then this, and then writing your own logic within each of those tasks to say how often it should happen, which is what I did in the air quality sensor. You simply say, this is a task and I want it to happen every 200 milliseconds, or whatever the interval happens to be. And the scheduler in the operating system has a list of these tasks and it knows how frequently they have to be executed. Now, there are complications that come in because what we're talking about here is starting to border on a multitasking operating system like Linux. The big problem with that is what happens if you have two events that are meant to occur at the same time. So you need some kind of a prioritization system. And you might say, I want to read from this sensor every 10 milliseconds and I want to publish to MQTT every 2 minutes. So they're operating on very different cycles. But if the scheduler gets to the point where it says, okay, this one is due to be run and this one is due to be run, there needs to be some kind of an arbitration process where it decides which one to run. And this is really the task that something like a real-time operating system is solving, because there are times where you will have tasks that are extremely time critical, and other times you'll have tasks that are not time critical. For example, if you are running a system that is analyzing an incoming data stream, things like the timing of the pulses can be critical. So you might have a task which is watching for a bit stream, and it will have rising edges and falling edges, and there'll be the duration of the pulses. This could be something like reading an infrared signal from a transmitter. So you have an IR receiver on your device, and you have a transmitter like an appliance remote control, like a TV remote control. You press the button, and there will be a series of pulses that are sent as an infrared signal, which are picked up by the receiver. And the timing of the pulses is obviously critical. If you are measuring the duration of a pulse and you are not paying attention at the right moment, you might misread the message. So the timing on that sort of thing is critical. Whereas the timing on, and if you are wrong by a few milliseconds, that could cause the whole thing to fail. Whereas something like reporting to MQTT, if that gets delayed by a couple of seconds, most of the time, who cares? There are times that it does matter, but most of the time it's not so timing critical. So the job of the RTOS is to prioritize these different things and to run them as independently of each other as possible and prioritize the things that need to be done quickly. And it's one of the differences between an RTOS and a full multitasking operating system like Linux or Windows or Mac OS is that the objective with an RTOS is to guarantee as much as possible that things will be executed when they need to be executed. Now, the way Linux work is that there is a thing called a tick timer in the kernel, and it allocates a certain amount of processor time to a task. And this is a preemptive multitasking model. So it says, I am going to be, like in the case of Mac OS, for example, on my machine here, it'll be saying, I'm going to allocate a certain amount of CPU time to Fusion 360. And then Fusion 360 does what it needs to do. And then the CPU says, oh, that's it, not doing you anymore. I'm now going to allocate some time to OBS. And then time goes by and it's like, oh, that's it, stop. I'm going to allocate time to something else. And it loops through those based on the tick timer, which I think by default in the Linux kernel, this is years since I've looked at it, but I think it was 100 Hertz. So it would context switch 100 times per second between all the different things that you were running. Please, someone correct me if I'm wrong about that. I remember a long time ago compiling a custom Linux kernel and changing the tick timer because I wanted the response of the kernel to be faster. So I didn't want it to have to wait potentially, you know, 100th of a second for something to complete in order to get onto a different task. So I think I can't remember. This is a long time ago, but I think I turned the frequency up to like 1 kilohertz or something instead of 100 hertz on the thing, which means you incur a penalty because you got a context switch more frequently, which takes time. So the overall efficiency goes down. Systems generally are more efficient if they can focus on doing one thing uninterrupted and then change context and save the state of all the registers and everything, and then do something else uninterrupted for a period of time, and then context switch. And it's like humans. Every time we change a task, we've got to change our brains into a different mode of thinking and change what we're doing. You lose time in changing what you're doing. The computer is the same. So by running the tick timer in the kernel at a higher frequency, it means that it's switching between tasks more frequently, which means that each task doesn't have to wait as long until it gets processed, but you take an overall efficiency penalty because it is spending proportionally more of its time doing those context switches. I get the feeling I'm so far off on a tangent now. The question was just what's the difference between an RTOS and raw C? And now I'm talking about Linux kernel scheduling. Hopefully this isn't too boring. All right. Let's get back to this. Aaron asked another good question, which is, what's your thoughts on web-based programming languages coming to embedded devices like JavaScript? What are my thoughts on it? I think it is... Okay, the very brief summary is, I approve. And that's not necessarily because I'm going to use it myself, but I approve because it opens up the way of solving problems in more ways and making things and opening them up to people who come from different backgrounds. Now, I know there are people who actually argue the exact opposite for the exact same reason. One argument that I've heard is that it's a way of dumbing things down, as if, you know, JavaScript is somehow a language for people that are not as smart or something, which is silly. And I've heard people worry, well, if you can write microcontroller code using JavaScript, then it opens it up to people doing all sorts of silly things, and we'll see all sorts of broken projects and lots of security problems and instability, and you don't understand what's going on under the hood because everything is so abstracted away by the JavaScript interpreter compared to writing C. And I understand what people are saying when they make that argument, but I always err on the side of inclusiveness. I would much rather see people able to achieve things with the knowledge they have and the tools they have than to have people blocked out, like in a gatekeeping sort of fashion, like saying, you must learn C if you're going to use microcontrollers. I mean, if you're going to get heavily into microcontrollers, then learning C is almost a given. It's like the standard way of dealing with things. But it doesn't mean it's the only way. And it also should not be the barrier or the brick wall that you have to get through before you can do anything at all. So if you have an experienced C developer and an experienced JavaScript developer, and they both sit down to solve the same problem on a microcontroller, one using C and one using JavaScript, there will probably be differences. There'll be differences in a number of metrics in terms of how efficient the end result will be, in terms of how quickly the result is achieved. There may be circumstances where developing in JavaScript is faster. It's more efficient in terms of the developer time, but not necessarily as efficient in terms of the execution time on the device. So I love it when I see people doing new things and learning new things and taking knowledge that they have and being able to achieve things that they didn't think was possible. So the idea of someone coming from, say, a web development background, and they might know JavaScript fairly well and want to blink an LED or get into some kind of an embedded project, if they can use JavaScript to solve that problem, that's fantastic. Go for it. I really think that's a good thing. So I'm thinking back to the backlash that Arduino got in the early days, and in fact still gets. So many. If you went onto AVR Freaks, for example, 10 years ago, and any time that, like, basically Arduino was a dirty word, and the whole thing was, oh, these newcomers that are using Arduino boards, they don't have a clue what's going on, they don't understand the low-level registers, they're just setting pin mode and it does everything for them. They're idiots because they don't understand that what this is doing is actually setting the flags in these particular data direction registers inside the AVR, and that is then affecting the particular I/O. You know, those sorts of rants were just everywhere. And someone who wrote code in the Arduino IDE using the Arduino software environment, so the Arduino libraries and everything, and used calls like pin mode and digital write and digital read, were really looked down on. And now, to some extent, what we're seeing is the next level of that, where people who develop using Arduino see people coming along and using JavaScript, and they're saying, oh no, you've got to learn Arduino because, like, they don't understand that when they use this particular call in JavaScript, it's actually, so it's all just repeating. And it's it's kind of gatekeeping, and I don't like it. So my summary is, use whatever tool you like, whatever makes most sense to you. There are some tools that will be better at some things, and there's certainly knowledge that if you learn how to do things using a tool you're not familiar with, you may be able to achieve a better end result. But it's better to do something than to not do it at all. Anyway, oh, Harry said, do you think it would make sense to apply fuzzy logic to home automation? Okay. I assume that by fuzzy logic, what you're referring to there are things like machine learning and adaptive systems that do not necessarily have very specific black and white rules. Or they may have rules that develop in a semi-automated way, so you haven't necessarily set them up. And I think it has its place, but it can lead to some difficulties. So this is something that it's such a big topic that my head is buzzing about where to even start talking about this. I've got so many different angles on it. So for people that have been working in machine learning for a while, once again, you end up with the situation of, I have this hammer and I'm going to use it. And machine learning is a fantastic tool to use in the right place, but not everything is the right place. So there are certain aspects of home automation that I think machine learning could be really, really useful. There are at different levels of complexity. For example, machine learning could be used to tune the responsiveness of an HVAC system to be able to adapt to things like different climate conditions versus people in the house and different things that are running, and like all these different inputs that go into it. And you could conceptually have a system that learns over time so that it maintains the environment in the house at the most appropriate level in the most efficient way possible. I mean, I'm just kind of making stuff up here. And of course, there are things like the application of machine learning to face recognition. You could use face recognition to have a system that adapts to who is in a particular room, and it can be really useful for that. So machine learning can be used as a component of a system that provides information to other things. For example, if you had, say, Home Assistant or OpenHab or whatever high-level system you want that's running your house, one of the things that would be very useful for it to know is who is in the house and where they are, so that it can do things like set environmental controls and set music playlists and turn on lights and all of those sorts of things. But it doesn't necessarily need to know how that information is obtained. If you can build a system excuse me, that uses machine learning to be able to recognize, based on some inputs, which could be video, could be whatever, that this person is in this room of the house, and then sends that as a result to the home automation system, what you're doing is using machine learning to solve a particular subset of the problem and generate an answer which is then sent to the system that can act on it. So I think things like machine learning definitely have their place in solving problems that are very hard to solve in other ways. And something that I've noticed over time, or an idea that I've become more and more accustomed to, is the idea that a lot of the sensing problems that we try to solve can be solved by pointing a camera at something. And things like motion detection. You know, if you've got a passive infrared or a radar motion detector in a room, you can solve that camera by pointing a camera at the room and then processing the image, and you can detect motion. Now, obviously, there are big privacy issues. Anytime that you introduce cameras, you've got to think about privacy. But, okay, but lots of things like letterbox detection. So detecting when a letter is inserted into a letterbox. The detection system that I had many, many years ago, so 20-ish years ago on my letterbox, used a reed switch and a magnet attached to the flap on the letterbox. So when someone put a letter in, it would move, the reed switch would be deactivated because the magnet would move away, and then the letter would go in and you could send a notification. So it used to send me an SMS when I got a letter delivered. But that same sensor, that problem could be solved by having a camera in the letterbox pointing down, looking at it, and you could have some machine learning to be processing it. Now, that is a super heavyweight solution when a switch will probably do the job. But and you probably wouldn't necessarily do it that way because it's just it's using a sledgehammer to crack a nut. But the point I'm making is that there are an awful lot of problems where you can scratch your head thinking about how am I going to detect this certain thing, or how am I going to put a sensor here to determine this, that can be solved by just pointing a camera at it and using some machine learning and then giving an output when that condition is detected, which could be whatever, like something sitting in the letterbox, or a person in the room, or a door is open, for example. You could also detect that from the camera rather than having a sensor on the door. So machine learning has its place. Okay, now coming back to this though, and I'll wrap this point up in a second. The major this big house, the one that I keep talking about, had a very interesting thing happen to it, where there was some strange, it's what you would call emergent behavior, I suppose, where a number of subsystems within the house started fighting with each other. And my friend Andy, who is the one that was working on this house for a long time before I got involved with it, told me this story, and he would be able to tell the details correctly. I'm relaying information from many years ago, secondhand. In this particular house, it's got 3 swimming pools. One of the swimming pools comes halfway into the living room. So the living room was huge, and it was kind of a U shape with a swimming pool in one part of it. And then there was a big door that you can think of kind of being like a garage door, like a 2-part garage door, or a multi-part garage door, but it was much, much bigger. It was like a small aircraft sort of size, like hangar sort of size door, which was glass. And there was an outdoor pool as well, just on the other side of it. And when this door was open, the lounge room, the entire lounge room wall was open, with the swimming pool in the lounge room, and then it was joined to the swimming pool on the outside. So the door could be open or it could be closed, and then you'd have an indoor pool in the lounge room, and then there was the pool outside was separated off. Now this raised a few issues from a climate control point of view, because the indoor pool obviously would cause huge humidity inside the living room. And the home automation system had control over the main door, whether it could open or close. And there was a sensor across it, because there was for a while at least, there was a cat living at the house, and they didn't want the big door to close while the cat was underneath it, so it needed to be able to detect obstructions. And so the home automation system had data coming from the environmental sensors, so it knew about the humidity and the temperature in the room. It knew whether the door was open or closed. It knew the desired temperature of the pool and of the room, and it had control over the heating and the cooling. And I'd have to ask Andy to remind me of the details of this. But what happened was that they started seeing some really weird things happening. Like I think it was that when the door was closed, the heating on the pool would be activated and the cooling on the room would be activated, so it would be running the air conditioning flat out because the room air conditioning was fighting against the humidity that was being generated by the pool that was being heated, and it was cooling down the room, which was cooling down the water, which meant that the pool was trying to be heated as quickly as possible, and so different parts of the system were fighting against each other. And they started, I think what was happening was that the door was being opened or being closed unexpectedly, because the system was thinking, oh yeah, there's too much humidity in here, I've got to open the door. So the huge door on the side of the lounge room would just open. Anyway, I'm not really telling this story very well, so I will shut up now. Alright, back to the comments. So yeah, anyway, that was all. The reason for that was, the reason I mentioned that was that that's an example of an emergent behavior in a system. It wasn't using machine learning in that case. It was just taking different inputs, and it had multiple objectives that were in conflict with each other. So it was then doing things unexpectedly. And with machine learning systems, you can have that as well. All right. Scott said, let's all get back to proper programming. If you can't translate opcodes to binary in your head, go home. Yeah, I haven't done that for so long. I don't think I've ever translated opcodes to binary in my head, but it's I haven't done anything down at the machine code or opcode level for quite a long time. I used to do a little bit of machine code programming on a Z80 way back. In fact, I still have my first ever real computer. Maybe I should go and grab it, because it is just over in the corner of the room. I'm going to take this microphone off for a second and go and grab my first real computer. And have a drink before I put the microphone back on. How am I going to do this without getting myself tied up? I think this will work. Right, so this was the first proper computer that I owned, if you can call it a proper computer. So that is a Tech 1C, which is a talking electronics computer, and hopefully things won't fall off. It's a Z80 based system. You can see there's a hexadecimal keypad on, well, kind of in the middle of the screen. It's on the right hand side of the PCB, and you can see 6 7-segment displays down the bottom. There are 4 for the address and 2 for the data. And the processor is up in the middle, and if I had another hand I could point at things, but I can't. There's an expansion board up the top which has got an LCD on it. There's a bus kind of in the middle, which was a super dodgy thing that I did to extend the address and data lines so I could plug in different peripherals. Up the top is a relay board. It's only got 1 relay in it, but it can take 8 relays, and you can actually see right through the PCB. It's a single-sided phenolic PCB, and I would have done that using a resist pen. And then there is an expansion board over on the side that I also did, so I etched that. And when did I do this? I must have been about 15 years old when I made that, and then expanded it a little bit over time. And it had been sitting at my mum's house for years in the basement in storage, and I pulled it out a couple of years ago because I thought it'd be cool to try to resurrect it. the EEPROM has probably lost all its memory by now, so I'd need to load a new monitor into it. But that was my first proper computer. So that was all programmed by entering Z80 machine code in hexadecimal using that keypad. So what you would do is, well, what I used to do was I had a sheet of paper and I would write out my program in machine code, just writing the hexadecimal on the paper, and then so the address and then the code that you wanted into it, the commands. And then what you would do is use the increment button to go to a certain memory address, and then you type in the hexadecimal machine code, and then you'd store it, and then move on to the next address, etc. And then you could execute it, get it to run through. Okay. Scrolling back. Oh, I've missed so many comments. I'm trying to keep up and I'm just getting further and further behind. Alright. So, I'm seeing a few interesting ones which I will get to. Alright. Where are we? Oh, Seabreeze said, when I did my degree in EE, we got forced into Pascal and Fortran. Worst of all was programming 6800 micros in hex via a keypad. Very close to what I was just showing, back what I was doing when I was an early teenager. So, except that is a Z80 instead of a 6800, but I did 6800s at uni as well. Yeah, oh, and Frank said, late 80s, I did Z80 course programming in hex code. Great fun. Yes, Frank, you know exactly what I'm talking about. Oh, and Allsop69 says, I'll hand up some pics of the PLCs and systems I worked with and posted on Discord. That would be awesome. One thing I really love seeing on Discord, oh, in fact, there's already some up there. I can see Allsop has posted a pic of a PLC cabinet. Looks like there's a DIN rail mount thing on it. I will look at that later. But one of the things that I really like about the Discord is that it allows everybody to participate equally. It's not just me here talking and showing stuff, but everybody else can post pictures and do stuff as well. So I really like seeing other people's projects. And there are some really cool ones that have been posted. So if you want to look at what other people are doing, make sure you go to the Discord. Okay. Al asked what 3D printer I use. I have a few 3D printers, but the one that I use on a day-to-day basis, and in fact I think it's been sitting idle for more than 24 hours now, which is very unusual, is a Prusa i3 Mark III's. That's the one that you can see there inside an enclosure, and so it's inside a lactable enclosure. These particular legs it's two stacked, so you can see there's one there, which is a normal height lactable, and then I made new legs for this one so that it would be a little bit higher, and it's got 3D printed mounts and things that join it all together. And those clear sides that you can see through are acrylic. So it is fully enclosed. Even though it looks like it's open, it's actually in an enclosure there. And then I've got hangers up the top for the reels of filament, and there are reels of filament down underneath here as well. And then there is corrugated tube, like electrical tube that comes from there, and it goes up the back, loops around, and allows me to feed filament from this area down here, which is also enclosed, up and feed it into the printer. So I don't have to have all the reels up the top, some of the reels are down the bottom. That printer has been incredible. The Prusas are expensive as printers go, well, as domestic 3D printers go anyway, but it's a sort of thing where most of the time I can slice something and then just hit print and it comes out and it works really well. So I also have a very modified Mendelmax V3, which is through that door. If you watched the live stream last week, it would have been sitting on the table right here because I was messing around with it. But where it normally lives is it sits on top of the fridge. There is a bar fridge in the corner directly behind this wall where all of these parts drawers are. In that corner, on the other side is a little bar fridge, and sitting on top of that is my Mendelmax. That is connected up to Octoprint, and the power for that is on a SON-off. So normally it's turned off, but I can turn it on by remote control and then connect to Octoprint and send a job to it. The Mendelmax is a lot faster than the Prusa, but it's got a few problems. It's also got a much bigger print bed, so I can print larger objects on it. But the bed leveling is pretty crappy, and the surface is not very good. I've got, at the moment, I've got a piece of borosilicate glass on it, and then I've got some like no-name brand build tack surface stuck on it, and the surface has got quite damaged. I was printing PETG on it, and the PETG bonded to the build tack so much that I just couldn't get it off. I had to use a blade to kind of cut it off, and it's damaged the build tack. What I really want to do is get a surface like the Prusa surface with the magnetic flex steel bed, but larger. I need a bigger one to go on the Mendelmax. The other one that you can't really see, hang on, I'll move this monitor. If you look up a bit, so I'm moving my iMac to try to get the camera to move. Right there, that silver thing, that is a MakerBot cupcake. That is, I think it was about number 152. So from one of the early batches of the MakerBot cupcakes. So that's super early. One of the very early DIY 3D printers. That one I don't have in use at the moment, but it's sitting up there because it looks cool. It's a bit of a historical piece. It uses the older style 3mm filament, and the build area is like that big, by about that high, and it's yeah, it's a bit of a mess. But I've been thinking I really want to get it running again, just for the fun of it. I think it would be cool to be able to send print jobs to that, have them come out of the old MakerBot cupcake. And apart from the fact that the wood has been spray painted silver, it is a totally unmodified original cupcake, which is probably almost a museum piece now. You can also see a couple of drones and things beside it. There's an autonomous car in the middle. That's a dingo car, which is like a donkey car, self-driving car, uses machine learning to process video and then drive around a track. Oh, and the other thing, last week we were talking about Geiger counters and detecting high energy particles. That thing just there, you can see that there is an orb. There's a white orb sitting on top of a box. It's behind another thing, but just at the back there. Inside the box there are 3 Geiger counters and a Raspberry Pi, and what it's doing is detecting and the 3 Geiger counters are inside metal tubes, and the reason for that is to kind of act as a filter so that only high energy particles will get through, and also to make it directional. So the 3 tubes are sort of in a triangle shape, and by detecting pulses coming out of the 3 tubes, it can react differently depending on the angle of of the high energy particle coming in. And then inside that orb at the top, it's got RGB LEDs, and there is also an audio amplifier in it. And so what happens is that when a high energy particle is detected, it makes a chime like a bong sound, and it lights up in different colors. So if you leave it turned, it's not turned on right now, or it would be going off like every few seconds. But that is a thing that can visualize when there are high energy particles coming through, which happens all the time. That was designed by a friend of mine named Paul in Adelaide, and it was used in an art installation a couple of years ago. What they did was, down on the side of the Torrens River, there is a, I think there's a casino or something, I'm not sure what the building is. Anyway, there's some big building with a big lawn area down on the side of the Torrens River. And they built a whole bunch of those little sensors and spread them out across this lawn area. So they were, I don't know, a few meters apart in a big grid. And you could stand back and watch it, and watch the different lights turning on, and you hear the bong sound. And the idea was that it was a way of visualizing the fact that there are these high energy particles that are traveling through us and through everything all the time, and you could stand there and watch this this big field of illumination and sound as the particles zip through them. Pretty cool. And I was lucky enough to get hold of one of his sensors after the display ended, or one of his complete units, and I've had it sitting up there for a while. I turn it on occasionally, and what I really wish is that it would ignore most things and just come on occasionally, because it's a bit too much to have it making noise and flashing lights a couple of times a minute. It's fun for a little while, but you can't leave it turned on all the time because it just drives you nuts. So, summary is, I have 3 3D printers. One of them I use constantly, one of them I never use, and one of them I use occasionally. And I would use it more if I could get a better heat bed on it. Okay, oh, Cheetah Kid said, I didn't have computers in school. My first computer in 1982 was Sinclair ZX81. Yes, the classic 81. And the ZX80 that came before it. The ZX81 was fancy because it was in a black case. The ZX80, I think, was like the beige colored one. And that was the ZX80 would have been, I think, the first computer that I ever actually touched and used. And I haven't seen one of those for so long. But the first computer I actually owned and could control myself was this one, the Tech One. And the really cool thing is that back when I was playing around with the Tech One, there were a couple of guys, the 2 main guys who designed that, who, like, I saw their names in Talking Electronics magazine, and their name is on the PCB, I think. And, you know, the sort of thing where you see people mentioned and their names, and they take on mythical status in your own mind. So the 2 guys who designed that, it was Ken Stone and John Hardy, I think. I can't remember the other name. When I was a little kid, it was like these were the gurus because they were so smart they could design something like that board. And the really cool thing is that now, all these years later, I'm in a Facebook group with both of them and talking about classic computer design. And one of them is now working on an updated version of that board. So there is a new version coming out, a new tech computer designed by the guy who designed the original board all those decades ago, but updated just as partly as a bit of a nostalgia thing, I think. Okay, let's get back to the comments. Guru said, I had grand dreams for the Vault project as far as accessibility goes, but realized pretty quickly that general user updating was going to be super problematic. Scaled that back big time. Yeah, so it's that is such a challenge. Trying to make projects that are easy for end users, both from a development point of view and from a user point of view, and being able to configure things, even with the simplest of systems. Just looking around now, because I was facing this problem just on Friday. Okay, once again getting into a tangent. Okay, so the problem that I was trying to solve on Friday, and I've been sort of thinking about it for the last couple of weeks, is the load cell button project that I've been working on with my friend Chris. The problem is how to configure it. What we've got is a device, so the 30-second background for people that haven't seen this. Chris has Duchenne muscular dystrophy, and he's just turned 42, so he is living way beyond any normal life expectancy for someone with this particular disease, and has progressed to the point where he has almost no strength in his muscles. He has about 10 millimeters of movement in his fingertips on his right hand, and he can only apply a very small amount of force. So one of the things he relies on is a nurse call button, so that when he's in bed, if he needs assistance with breathing or coughing or whatever, he can press the button and his carer will be notified and they can respond to him. The problem is that the nurse call button that he's been using, so it's a little button that puts a Velcro loop on it, so the Velcro loop holds it attached to his finger and it just sits there, and when he needs assistance he just squeezes it. The mechanical switch in it, which is just like it's kind of like a micro switch, it's like a little tact switch basically. If you push a tact switch, there is a fair bit of resistance before it clicks, and when you press it, it goes click. It's got a very distinct action, but it takes a not insignificant amount of force to activate it, and it's getting to the point where he has trouble activating the nurse call system. So we've been working on the system that uses a load cell, and it measures how much force he's applying, which means that it can be incredibly sensitive and it can be tuned so that it will trigger at a set point that is adjustable in software. Now, this gets me back to my response to the Guru of Nothing's comment, which is that we need in this ways to configure 3 options, and if we're going to have other people that are using this, we don't want them to have to install the Arduino IDE and change config options and recompile it and then flash the code just to change settings in it. I mean, that's totally unacceptable. So we need some way of having a user interface on this incredibly simple system. Well, an incredibly simple user interface. It's not actually a simple system, so that a couple of things can be changed. The obvious one is changing the trigger threshold. So whether you want to, so on the device, I mean, this would be so much easier if I just showed it to you, but where is it? I've got a couple of prototypes up there. I won't bother getting it out now. I'll rush through this story. The actual device is in use at Chris's place now, so I don't have it here. We need to be able to adjust the threshold, so we have a display on it and a knob, and it's a rotary encoder with a button. So you press the button to put it into alteration mode, and you turn the knob and you can change the threshold at which it is activated, and you press the button again and it saves the value to non-volatile memory and locks the button. So the idea is that if you come along and bump the knob, it is not going to change the setting. You can turn the knob, it won't do anything, because the worst thing would be if the knob was bumped accidentally and the threshold was increased, and then the person who is using it is trying to activate it to call for help, and it's not activating because they can't reach the threshold. So we've got it so that in order to change the setting, you don't just turn the knob. You have to press the button once to click it, and it puts it into a set mode, and then you can adjust the threshold, and then you press it again and it saves the set mode. And if you put it into programming mode and then you just walk away from it, after 30 seconds it times out and it defaults back to whatever it was before. So the idea is to minimize possible false entry. So if someone wants to change the threshold on the nurse call system, they have to very consciously press the button to put it into adjustment mode, turn the knob, and then press the button again to save it. And only then will it be changed. But there are also a couple of other options. One is pulse stretching. In Chris's case, he has a fair degree of control over the timing, and he often uses the nurse call button as a way of communicating intent. Like if something is a real problem, he's just going to grab it and squeeze it, and he's going to keep that buzzer going and not let go. But if he just wants to, for example, get someone's attention when he's in bed, he can just tap it and make it go beep and not, cause big problems. So the duration of the buzz can be important. So in his case, what he wants is instant response from the nurse call system. So when he lets go, it stops immediately. But some people don't necessarily want that. And an example of this is a multimeter. If you have continuity mode on a multimeter and you tap it together, if you tap on something, some multimeters will keep the beep going for a minimum period of time. And it could be quite short. In fact, your multimeter may be doing this and you don't even realize it. If you take the multimeter probes in continuity mode and you just tap them together, the duration of the pulse, if it's been detected, will probably be some minimal period, and it might be only 1/10 of a second or something quite short. But what it means is that it's not going to be just the 100th of a second of tapping the probes. If it's detected continuity, it will stretch the pulse long enough that you can hear it. And so with a nurse call system, you may want the same thing. So what we did in the software is put an option in where if you activate pulse stretching, it will turn on the buzzer for a minimum period of time, which might be 1 second or 2 seconds. So if you just squeeze it briefly, and if that's all you can manage, it won't just go beep and turn off, and then the carer might think it wasn't anything serious, it was just accidentally being bumped. What it does is it turns on the output and it keeps the output on for a minimum period of time and then turns it off. That defeats Chris's requirement because he wants to be able to control it and just do very brief beeps with it. And so we want that to be an option. We want the pulse stretching output to be something that can be turned on or off. Once again, it's no good to have someone install the Arduino IDE, change a config option, recompile the code, flash it onto the device just to change one option. So how do we make that as easy as possible? And what I was just thinking about on Friday was putting a physical switch on the device. So you just turn pulse switching on and off, and have the switch going to a digital input in the microcontroller so it can detect the position of the switch. That way, if someone wants to change it, they can. In fact, I think I will grab the prototype just so I can show you what I mean. And back here, somewhere here, I've got a prototype, I think. No, that one doesn't have it. On the... Oh yeah, here we go. What I've got on here, this is the control board for one of them. And it's a little bit hard to see, but down here there is a little slide switch. It's a tiny little thing, and it's set back from the edge of the PCB. It doesn't protrude past it. This particular switch is actually to change the output from normally open to normally closed mode, because the output of this, which comes out through this socket, would then be connected into a nurse call system. And nurse call systems, some of them have a normally closed input, and what that means is that if anything goes wrong, say a cable gets pulled out, that will cause the alarm to go off because the connection has been broken. But some nurse call systems are normally open input, so you have to close the circuit in order to trigger it. So what this little slide switch does is switch between normally open and normally closed modes on the output. And that is something that you would only ever change once when you're setting it up, depending on what you're connecting it to. And on the 3D printed enclosure, we've got a little slot on the bottom so that you can use something like a pen or a paper clip and flick that switch across into the mode that you want. So this is getting back to the user interface point. What I was just thinking about on Friday was adding a second switch on here, which could then control the pulse stretch feature. And that way, you don't need to change any code. It's just, you might want the pulse stretching, you might not, but you can flick the little switch underneath it. And when it's actually mounted like on the head of the bed, the switch isn't visible, it's just in a slot that's under the bottom of the case. But you can change it if you need to. It's something that you don't change every day. You typically change it just during setup and then never touch it. So you can flick the tiny little switch whichever way you want. Okay. Oh, this is a great comment. Ecognito3 says, a full stack programmer is someone who can write JavaScript for the front end and the back end. Yes, JavaScript, the universal solution from the top to the bottom of the stack. Okay, so I'm gonna wrap it up. It's we're well past 2 hours now. There are some really good questions in here, lots of comments that I want to get to. So one said, what strategy do you recommend for testing IoT solutions? How do you validate your own devices? That is such a good topic. In fact, I'm going to write that on my whiteboard. I've got a little list. Everything's backwards, it's confusing. I've got a little list on my whiteboard just here of things to talk about in future live streams. So I'm going to put IoT device and testing and things onto that list and come back to that, because that will it's not something I can answer in 30 seconds. Alright, I'm just going to scroll through here very quickly, see if there's anything else I want to add to the let's come back to that topic list. Oh, James asked how are the new light switchboards going. Pretty well, not right here. I did have them on the bench, but I did a context switch, so I moved them back into the container. So what I want to do is get a bit more of the air quality sensor project wrapped up, and then I'm going to do a mini series about light switches. One thing I do have right here is one of my smart switch prototypes from, when was this? This must be 2 years ago. Yeah, 2018. So this is an RGB illuminated light switch, and on the back of it, it's in two parts. I'll take this board off. There is a board that connects to the buttons, and it's got WS2811 RGB LED drivers on it. And the idea is that this particular board is specific to the number of buttons on the front. So this is a 4-way board. I can also do 3-way, 2-way, 1-way, and it just has like a different layout. But the interface is the same. There's a little header just here, and then the control board goes on top of it. And this board can be the same for all the different switch variations. This one's got a ESP12 module on it, so it's got an ESP8266 in it. And on the other side there is a RJ45 socket, and there's a little switch mode regulator, so it can do power over Ethernet. And what else is there? So it's a 5-volt switch mode regulator feeding into a 3.3 volt linear regulator. So we can feed up to 28 volts into this and it will be happy. And then this board mounts on here, and I'm just sticking it on the connector, but there should be mechanicals and things. Like you can see there are mounting holes there. So these two boards are attached together like in a sandwich configuration. and then it goes into the wall. You plug the cable in here, and what it does is take power off the cable using the same pinout as power over Ethernet, but it's not Ethernet. And the idea with this is that it's a drop-in replacement for my existing light switches. It uses the same connections on here, and it can, when you press these buttons, it shorts out the correct wire the same way as my current light switches. But the difference is that it's got an onboard ESP8266, which is controlling the RGB LEDs. And that means you now have the option of not just like a dumb switch that sends commands, but you can also do things like change the color of the LEDs, excuse me, to show the status of whatever the load is. So if you turn on a light, you can have it change color on the matching button on here. So yeah, I did these 2018. I still haven't even shown those in a video. I've got so many projects. Okay. I'm going to have... Oh, I'm so far behind in the chat. Okay, but the other part of that, so I was talking about that. The other part of that is the light switch controller. I think that was what the original question from James was about. And I've assembled a board. So last week on the live stream, we ran the pick and place machine and we populated a board. Since then, that board has had the big RJ45 sockets on it, the 8-way sockets, and everything else has been installed on it. And I've also soldered up, they're back in the box as well. I've also soldered up the new version of the Volt Hat, which has got the header on it to connect to it. And I've assembled a new version of the I2C control panel with the big OLED on it. So now it's a bit of testing and coding, but what I'm going to do is I think do a mini series about light switches after the air quality sensor series is finished. I've got 2 more videos to come out for that. The next one is going to be how to record and visualize the data that comes from the air quality sensors. So I'm probably going to cover, Grafana and those sorts of things. And then the final one will be the Pro version, which is the version, well, there are some blank PCBs here. This is the version with the ESP32 on it and the BME680 and the PMS7003 sensor, all in a little 3D printed case. But I've got to get those out of the way. I've got such a backlog of videos. All right. I'm going to sign off for now. Thank you so much for coming along to this live stream. It's really cool to have so many people coming along every Sunday. Every week I think, how am I going to get through 2 hours of doing a live stream? What am I going to talk about? And we get past 2 hours and I think I've got to just stop it. But it means there's more for next week. So thank you so much for coming along. I am going to mute myself in a second and sign off. Thank you. Bye.